So we are going to talk about Newton's law of universal gravitation. And I mentioned this a little bit in chapter 4, but we really didn't get into it. So we're actually going to go ahead and use it now. It's honestly really easy to use. You just have to plug numbers in. But I'm just going to kind of teach you how it works. So basically, if you have two particles with masses and they're separated by some distance r, we say that's the radius, then a gravitational force acts along a line joining them with a magnitude given by. So here's the formula. It's the force of gravity equals this constant g, and it has to be capital G so you don't mistake it with little g, which would be the acceleration of gravity. And then you multiply the two masses together and you divide by the distance between them squared. And so basically, I was telling you guys, I think earlier in the year, that any two objects that have mass have a gravitational pull toward each other. So this is how you figure out what that gravitational pull is. Now that constant g happens to be a really, really, really tiny number, which makes that force really, really, really tiny unless the masses are big. So any gravitational force between you and another object is going to be real small because your mass and the object's mass are real small compared to like the mass of planets and things like that. This also pertains to everything in the entire universe. So this is not just a law on Earth. This is a law for the entire universe, which is why it's called the universal gravitation. So G is the constant of universal gravitation, so they call it the gravitational constant. And its number, the constant, is 6.673 times 10 to the negative 11. So I told you really, really, really tiny. And then it has to be in newtons meters squared over kilograms squared. So you want all the numbers you put in to be in newtons, meters, and kilograms, so you don't mess up with this constant. And then this equation is an example of an inverse square law, and that just means that basically force is proportional to the inverse square of the distance between the objects. The gravitational force is always toward each other, meaning it's an attractive force, not a repelling force. So if you look at these two, so the force of object 1 on object 2 is written like this. The force on object 1 by object 2. And this one here is the force of object 2 on object 1. They're going to be equal. The forces on each other are going to be equal. You would figure it out by plugging into the equation. So you have mass 2, you have the distance between them, which would be r, and then you could figure out what the force would be. It's basically part of a action-reaction pair. And the last piece of this is really just a concept. You won't need to know much about it, but basically the gravitational force exerted by a uniform sphere, so that means that the sphere, all of its mass is distributed uniformly, so it's not like more massive on one side than the other. So the exerted by a uniform sphere on a particle outside the sphere is the same as if the force exerted on the entire mass, as if the sphere's mass were concentrated at its center. So it would be the same thing if you could take all the mass in the sphere and squish it into the center. It would exert the same force on a particle outside of its center. So because we have this force equation, of course, remember force is ma, so that means that we could figure out the acceleration due to gravity anywhere we want as long as we have the information needed, like the masses and the distance. So basically you just take away the second mass from the equation, and the acceleration equals g mass of the Earth over r squared, or in general the mass of the planet you're trying to figure out the acceleration for. So this should be the acceleration of the gravity on that planet would be equal to that equation. So you could figure out the acceleration on any planet. We also have a new gravitational potential energy. Before we were using mgh, but now since we're a little bit more clear on kind of the overall equation, we can be a little bit more specific. So we say that the potential energy when an object is not near the Earth's surface, so like somewhere out in the atmosphere or in space, like high above the Earth's surface, we can use this equation instead. So you wouldn't want to use mgh if you're talking about a satellite's potential energy. You would want to use this gravitational equation. So basically the rule of thumb is you would use it if the radius or the distance away is bigger than the radius of the Earth. So anything out above the radius of the Earth. Things fairly close, we can use mgh. Okay, we also have this thing called escape speed or escape velocity. And you might hear this talked about like in movies. I know they talked about it like I think in The Martian and maybe Gravity or whatever. And they talk about this escape velocity. And basically that's the speed that an object would need in order to get out of the planet's atmosphere and get into space and then not return. So basically to get out of the gravitational field of that planet. So of course there's always going to be some gravitational pull because of the mass, but this is the speed you would need to get out of the Earth's or out of a planet's atmosphere. So for Earth, it would be the escape velocity would be this. It'd be the square root of 2 times the gravitational constant times the mass of the Earth divided by the radius of the Earth. For the Earth, it's about 11.2 kilometers per second, which is pretty fast, which is why we need to send rockets up pretty fast. We can't just kind of slowly escape the atmosphere. Also notice that the velocity to escape is independent of the mass of the object. So whether it's a little tiny shuttle versus a big giant rocket, it doesn't make a difference. The escape velocity is the same. Here are just a list of some of the escape velocities for other planets. So it's kind of like one factor that determines the planet's atmosphere. The more atmosphere you have, the harder it's going to be to get out. Okay, so now we're going to talk about there's 3 laws that are called Kepler's laws, and they have to do with planets and orbits. So the first law is that all planets move in elliptical orbits with the sun at one of the focal points, and we will go into more detail on each one of these. The second law is that a line drawn from the sun to any planet sweeps out equal areas in equal time intervals. And the third is the square of the orbital period of any planet is proportional to the cube of the average distance from the sun to that planet. So, and this is just kind of a side note, but Newton demonstrated later that these laws were actually just consequences of the gravitational force between the 2 objects. So all the results we're seeing are just because there's a gravitational force between the 2 objects. So the first law basically says that all planets move in elliptical orbits with the sun at one of the focus of the elliptical. So if you remember the geometry of an elliptical, then or an ellipse, then this is going to be a little bit easier for you. But basically, there's a focus at one end, a focus at another end, and the sun is going to sit at one of those foci. Any object bound to another by an inverse square law will move in an elliptical path. So the second focus is going to be empty. Here's the second law. So it says a line drawn from the sun to any planet will sweep out equal areas in equal time. So the area from A to B and D to C are equal. So this area right here is equal to this area right here. And the planet will cover that amount of space in the same amount of time that it covers this amount of space. So you notice this is a shorter distance, a shorter arc length than this one. So that must mean that the planet must be going faster over here when it's closer to the sun. So the planet moves more slowly when further away from the sun, and it moves more quickly when close to the sun. And then the third law says that the square of the orbital period, so the period of the planet squared, is proportional to the average distance from the sun to the planet cubed. So t is the period, the time required for one revolution. We remember that, right? So for Earth to orbit the sun takes a year, so that's the Earth's period. For the orbit around the sun, so basically that's what we figured out here. K is this number, it's just a constant, but basically it's going to change depending on which sun you're using, which planet you're talking about. So K is independent of the mass of the planet, and I'll give you a more detailed equation in a little bit. And then A is the average distance from the sun to that planet. So here's a little bit more useful of a equation, but it can be used to find the mass of the sun or a planet. So when the period is measured in Earth years, and the semi-major axis is in AU, which you don't really need to worry about, Kepler's third law has a simpler form. It looks more complicated, but so basically it's just 4 pi squared over the gravitational constant times the mass of the sun multiplied by the distance from the sun to that planet cubed. And so you can see that you can find kind of a lot of things. You can find the mass of the sun, you could figure out the distance from the sun to the planet, or you could figure out the period of the planet. So a geosynchronous orbit, this is just kind of talking about satellites. Geosynchronous orbit means that the satellite or the object will remain in the same place on the Earth. So basically it's going to watch one spot, or it's going to be located above one spot on the Earth. So it will have the same period as the Earth. And then we say that the radius of the satellite would basically be the height of the satellite above the Earth's surface plus the radius of the Earth. So don't forget, we're talking about from the center of the Earth, so we have to include the radius of the Earth when we do when we look at the radius of a satellite. Okay, so here's an example. So it says find the gravitational force of the Earth on the Moon if the average distance from their centers is 384,000 kilometers. So we're going to use this equation. Oops. And we're just going to go ahead and plug in. So G is going to be 6.673 times 10 to the negative 11 times the mass of the Earth, which you guys will actually memorize eventually, but it's in your book, like a couple pages before the homework. So it's actually 5.98. 5.98 times 10 to the 24. It's supposed to be a 10. And then times the mass, and let me put this down here, the mass of the Moon, which is 7.36 times 10 to the 22. And then you would divide that whole thing by the radius squared, which would just be their average distance squared. So I want that in meters. Remember that the G is in meters, and so I'm going to have to make this 384,000,000 meters squared. And so if you do that math and you plug in, you should get your answer. Okay, let's do one more example. So I just want to show you guys how we're going to use that Kepler's third law equation. So a satellite of Mars has an orbital radius of 9.4 times 10 to the 6 meters, and a period of 2.8 times 10 to the 4 seconds. Assuming its orbit is circular, find the mass of the satellite. So remember, our equation is t squared equals 4 pi squared over g times the mass of the sun, or the mass of Mars in this case, times r cubed. So if we plug in, we're going to have, whoops, let's plug in for t. So we'd have 2.8 times 10 to the 4th squared equals 4 pi squared over g, which you guys know is 6.673 times 10 to the negative 11 times the mass of the Moon, or I'm sorry, the mass of Mars, which is 6.268, so it's kind of long to write, but 6.268 times 10 to the 23rd, and then you'd multiply that whole thing by r cubed. So you'd multiply by 9.4 times 10 to the 6, that whole thing cubed. And then you should be able to get your answer. So it's really just a lot of plug and chug. It's nothing like intense or anything really difficult to think about.